Here's a little warm-up for you to try for this. Try this on your own without any help from me or anybody else. Find a function capital F. Find a function capital F whose derivative is lowercase f of x equals 3x squared. Now that's probably not that hard to do. Here's the trick though. Well, not a trick. I want each of your answers to be different. So get with your little partners around you, and each of you have to have a different answer.
Good, I called it.
Go, talk about it. Talk about it. Hey, when I first asked this question, what was your first thought?
X to the third.
Probably everybody's first thought for capital F. So let's do capital F of x. I would assume it was probably x to the third for everybody.
Yeah.
Yeah, but once I said everybody had to have a different answer, what is that? So if we added, could I add anything I wanted, like 3x squared?
No.
What did it have to be?
A number.
A constant?
Yeah.
Why? The derivative of a constant is? Zero. Okay? So anyway, let's just assume, though, that the first go-around we all had x to the third. Okay? This right here, that's your antiderivative. Okay? So write this down. The function capital F, make sure this is a capital F. The function capital F is the antiderivative, is what it's called, of lowercase f. And how do we know that it's the antiderivative? Well, what if we took the derivative of capital F? What do we get? 3x squared. Okay. We've already learned how to take derivatives to go from this way to this way, or from this direction here to that direction. That's called differentiation. Integration is going backwards. You start with this and end up with that. That's integration. Okay. Integration techniques help you find antiderivatives. Okay? You with me though still?
What would you use?
Well, for example, who's taking physics in here? You've gone from position functions to velocity functions to acceleration functions using differentiation. Well, what if you had an acceleration function and you wanted the velocity function?
We always just do by the
You would go backwards using integration techniques. Anyway, so let's just write this more formally. A function capital F is the antiderivative. This is a formal definition. Antiderivative of lowercase f if you guys might be able to tell me this, if what?
Capital F is the derivative. Wait.
Keep going. How do we know that capital F is the antiderivative of f?
If lowercase f is the derivative
of lowercase f.
Close. I think we got to switch that around though. The derivative of capital F is equal to
that's
Little f, right? Isn't that what we just showed? So capital F is an antiderivative if you take the derivative of it and it equals lowercase f for all x. Okay? But what you guys just were able to do there without much problem was there a unique antiderivative?
No.
Didn't we all have different ones?
Yeah.
So the antiderivative doesn't necessarily need to be unique. So write this down. This is a theorem. If capital F is an antiderivative of lowercase f, then capital G is also an antiderivative of lowercase f if, here's a little shortcut for if and only if you do two f's, just by the way. That means if and only if in shorthand. If and only if G is of the form G of x equals capital F of x plus C. Isn't that what you guys just did? You took x cubed and added some constant C. Okay? So as long as capital F is adding or subtracting some constant, that means anything you can come up with is also an antiderivative. Yeah. Where? That's a... Yeah? So anyway... So technically, write this. Technically, the antiderivative, so we need to amend what we just had initially. Technically, the antiderivative of f of x equals 3x squared is capital F of x it's x cubed plus what? Plus anything, plus c. Yep, so it's x cubed plus c, where c is a constant. So all of you, I'm sure, had some x cubed plus 2, x cubed plus 10. I would have thought of x cubed plus pi. Did anybody have that one? You did? Yeah! X cubed plus pi.
I did. The fourth root of x to 12. That one was like way back. Way back.
I did x cubed plus 0 on x.
I did.
Wait, hold on.
Go 1/3.
We have a question. Ben, go ahead.
For me, I just did 3x cubed over 3.
Yeah, sure. Yeah. Yep. Okay, so let's talk about differential equations. We've actually seen these before in section 3.9, where we approximated the change in values using differentials. Remember that?
Yeah, with percent error.
With percent errors. So here's example 1. Find the general solution to the differential equation y prime equals 2. Now this is just a difference in notation. What does the prime mean? That this is the derivative. So what we need to find is the antiderivative, whose derivative would be this, if that makes sense. Keep going, 2x. Did you guys all hear that? So we're going to not do y prime in here. We're going to do y equals. This would be the antiderivative. Y equals. And what kind of a function do we have to have whose derivative is 2? 2x, but it says the general solution. So it's 2x plus c. This is what's known as a differential equation, you guys. You saw it like this back in 3.9. dy equals 2 dx. You would have seen it this way. Does this look familiar? Okay, dy could be the same thing as y prime. Anyway, those are all called differential equations. So the point here, I know this was really easy, but the point was, what's a general solution? It has plus c. That's the general solution. Okay? So, what was the second objective? We did, that's objective 1, find the general solution. We move on to objective 2?
Yes.
Okay, objective 2 was indefinite integral notation. Here we go.
Alrighty.
Indefinite integral notation. So what we just solved, y prime, let me go back to this, y prime equals 2. Okay, write this, that's the same as dy dx is equal to 2, right? But back in 3.9 we moved the dx over, so you could write this as dy equals 2 dx. You still with me? So write this phrase down. The process of finding solutions to this kind of equation, I'm talking about differential equation, to this kind of equation, like the one we just did, is called indefinite integration. So I used a specific example using 2. Let me use a more general example. You guys watching? So let's say that dy dx equals some function f of x. That also means that dy is equal to f of x dx. Do I need to slow down? Are you all right? Well, I'm not done yet. You with me up to this point? Okay. Now, if we started with y prime or dy, wasn't the point to actually find y itself and not dy? Isn't that what we did in this last example here? We had y prime, we wanted y itself. Okay. That process is called indefinite integration, and here's the symbol for it. Okay? It's an elongated S. Okay. And I think after the next lesson you'll understand where the S comes from. I'm not going to get into it today. Okay. But if you see this symbol right here, you guys, this symbol means you can integrate it. The integral of dy is equal to y. If you take the integral of dy, that's equal to y. It's the antiderivative, essentially. The process of finding an integral is antiderivative. The derivative, or the integral of little f, is capital F of x plus. What did we always add to the end of the general solution? C. Well, the d of x was just that change in x that came from over here. You'll see after we do this that that has no bearing really on capital F of x after we do some specific examples. What is this called? The general solution to a differential equation, yes, but it's also an antiderivative. What's the process called? Indefinite integration. Okay. So here's some basic integration rules. Oh man, there's a bunch. Okay. So let's just go through them so you have a list of them. We just got to get through this. Okay, you ready? First one here is the integral of 0 dx. What kind of a function would have a derivative of 0? A constant. So if we're reversing this process, what kind of a function here would I have to be?
C.
Okay. Just some constant.
Oh, that's where that S comes from. So like we're going to put numbers on the top and small on the bottom of that.
That's called definite integration.
Are you sure it's not for
Okay, second one. If we're taking the integral of k dx, now k is a constant. They don't want to use the letter c again, so they're changing to the letter k. K is a constant. No, the derivative of a constant is equal to 0, but we're reversing. So what kind of an antiderivative would have a derivative of k?
X.
Kx plus c. Okay. Third one. We got to start picking this up, you guys, so let's keep the chatter down. If you're taking the integral of a constant multiplier of a function, this resembles the constant multiple rule we learned for taking the derivative. You can just take the constant out of the process. So take the k out, and then you can find the integral of the function, f of x dx. That's really all that rule is saying, that if you have a constant in front of a function, you can take the constant out of the process and then take the integral. Okay, we good? We're going to do examples of all these here in a second. We got to get through all these rules. Okay. Fourth one, if you're taking the integral, indefinite integral, of the sum or difference of two functions. You guys are clever enough to probably figure this one out. What does this equal to? If we're taking the integral of the sum of two functions. We just split it apart and take the integral of each one. Isn't that what we would have done with derivatives? So most of these rules mirror the derivative rules. So this would be equal to the derivative, or sorry, the integral of f of x dx plus or minus the integral of g of x dx. Not really, no. The integral of x to a power. Ooh, you guys are going to have to think about this one.
It's a power to a power.
So if we were taking, let me go back here. If we're taking the derivative, let's go back to derivatives of x to the n.
NX
Isn't that nx
to the n minus 1.
to the n minus 1? That's the derivative rule we learned a few months ago. So what's going to happen here? With derivatives, we decrease the power, didn't we? So with integration, we're going to have to add to the power, right? You guys seeing the similarities here? So it is going to be x to the n plus 1 over n plus 1. And again, I know these general rules don't mean much to you now. We're gonna do specific examples. We just got to get through these. Okay? I think I am. Ooh, I am. Yes. Thank you for reminding me, though. Plus c. Yep. Now, n does not equal. N cannot equal negative 1 here, you guys, because you'd be dividing by 0. That doesn't work. Here's going to be your favorite ones.
Oh, yay.
Your trig rules.
Oh, you said that would be our favorite.
The integral of cosine. Again, these mirror the derivative rules. So it's going to be sine of x plus c. We're just going backwards, aren't we? So for the 7th rule, the integral of sine, whoa, I missed an x, cosine x dx. And then the integral of sine x dx. Well, we have to decide, is it cosine or negative cosine? Let me first put positive cosine. So if we're claiming that this is true, then the derivative would have to be negative sine, right? But here we have positive sine, so it is going to be negative cosine x plus c. The integral of secant squared dx. This is going to really test your memory. What is secant squared the derivative of? Tangent. This is going to stretch your memories here with these dang old trig derivatives. The integral of secant x tangent x dx.
Secant.
That's the secant. Two more. These are basic integration rules. This is the first round of integration rules. There are a lot more to come. Not in this section, but
We're going to memorize all of them.
the integral of cosecant squared x dx is negative cotangent of x plus c. And finally, cosecant of x, cotangent of x dx is negative cosecant of x plus c. Holy shoot! Yeah. Our brains are full.
I think I need to like bulimic the brain right now.
You need to go bulimic on your brain?
Yeah. Just like
That sounds so terrible.
and then like start getting some real
That sounds awful. Find each antiderivative. You ready? Let's start with this one. Shut it. Let's go. You guys are making this take way longer than it needs to. So I'm asking you to find the indefinite integral of 3x dx. So, let's take a look at some of our rules here for a second. First of all, that 3 that's in front, that would be like this integration rule, the property 3. We have a constant multiplier, so I can take out that 3 and put it in front. You guys all right with what I just did there?
Yeah.
That's called the constant multiple rule. You can take out a constant. If it's multiplying, you can take out a constant. Alright. Now, this x is really, you really need to think about this as x to the first power. Now go back up and look at your rules. Do we have some kind of rule that describes x to a power? It's the fifth property. What do you do with the power?
add to the power.
You add, and then you divide by whatever that power is. So the integral of x to the first power dx is what? X? Come on now. X squared over 2.
Yeah.
So then the antiderivative would be just a plus c at the end, because it would be true for any constant. So yeah, it'd be more common to write it as 3x squared over 2 plus c. Not that they would probably ask you to do this on your homework, but just because we're barely learning this, how do we verify this? Exactly. What if we took this now, 3x squared over 2 plus c, and took a derivative with respect to x? What would we expect to get?
Yeah.
We should get 3x. Do we get 3x?
Yep.
Take the derivative, you drop down the 2, but wouldn't that 2 cancel with that 2?
Yeah.
And what's the derivative of a constant? 0, so the derivative equals 3x. Okay? Let's do a few more, since we're having so much fun. Part B. Evaluate or find the antiderivative. Alright, we're kind of jumping the level of difficulty here quite a bit. Didn't one of the rules say if you're taking the integral of the sum of terms, you could split that up into different integrals?
Yeah.
So this could be the integral of 8x cubed dx minus the integral of 9x squared dx. This was this one where you had the sum or difference. You could just split that up into different integrals. Plus the integral of 4 dx. So, what should we do with this 8?
Well, let's take it out.
Take it out. So this is 8 times the integral of x to the third dx. What about this 9?
Well,
You take out the 9, so it's minus 9 times the integral of x squared dx. This 4, I'm just going to leave it where it is. I mean, it is technically multiplying dx, but it's not multiplying x or anything like that. So what is the integral of x to the third? Remember, you increase now the power by 1, and then you divide by that same power. So it's going to be 8 times x to the fourth over 4, which eventually will give us 2x to the fourth. Now we're going to subtract.
And where's the dx go?
Once you take the integral,
Oh.
the dx is gone. So the 9 isn't part of the integration process. We took it out, so it's just going to stay 9. So it's 9 times x to the third over 3 plus 4x plus c. And then simplify. 8 over 4 is 2. 9 over 3 is 3. And I hope you guys are good enough at derivatives that verifying this isn't going to be too much of a big deal. If we just quickly imagined taking the derivative of this, wouldn't we get 8x cubed minus 9x squared plus 4? Is that what we started with?
Yeah.
So these, for the most part, aren't terribly difficult to verify. We still good? Just kind of switch gears here. New example. This is a different section of your homework. This would be the directions. Find the solution.
Recharge.
Find the solution. dy over dt equals 9t squared. Now, you guys, this is a differential equation. Okay? So you need to move the dt over to the other side. So first thing to do would be to rewrite this as dy equals 9d squared dt. What they mean here is find y. We know dy equals 9t squared dt. How do we find y? We integrate. We do indefinite integration. What is the integral of dy?
It would be
1.
Okay, let me explain this here so that I'm sure there is less confusion. You guys, shh, 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 shh. What does this little d stand for?
the derivative.
The derivative. The integral is the opposite of a derivative, right? For the most part. So if you integrate something that's being, or something that you're taking the derivative of, Those are opposite or inverse operations, pretty much. So the integral of dy is just y. But you have to integrate both sides.
Okay.
So y is equal to the integral of 9t squared dt. And this just turns into a problem like we had just barely practiced. How do you find the integral of 9t squared dt?
You gotta get out the 9. Pull out the 9.
Take out the 9 and then take the integral of t squared dt. So it's t to the third over 3 plus c. So it's 3t cubed plus c. So when it says find the solution to a differential equation, really what they're asking you to do is use integration techniques.
It's only like
Here's where your God-given gifts of cleverness are going to come in handy.
Yeah, I've got 4 of them.
Yeah. This is one reason why students perceive integration to be more difficult. It really isn't. But for reasons like this, you have to kind of be clever about things before you integrate. So this is rewriting before integrating. Actually, you know, it's kind of like those limits we just practiced. Some of those limits you couldn't evaluate by direct substitution, right? So what'd you have to do? You had to rewrite it. You had to rearrange it. You had to manipulate it in some way. There's a lot of what's happening here. Okay? So for something like this, the integral of 1 over x to the third dx. Did we have a rule that looks something like this?
Maybe, isn't it 1/3 x cubed?
we don't. But we can make it x to the negative third.
Yeah, we didn't have a rule that looked like this, so just rewrite this as x to the negative third dx. Okay. Then you integrate. Once you've rewritten it, you integrate. So what's the integral? X plus c. Yeah.
Then you could move that x down, right, and do 1 over x to the second power plus.
And then you could write this as negative 1 over 2x squared plus c.
Would you care if we did either way?
No, I'd okay if it was like that. Another very, very common rewrite, and this is exactly what you had to do with derivatives, so this should be no big deal. But if you're supposed to find the integral of the square root of x dx,
X to the 1/2 power?
yeah, just rewrite that as x to the 1/2 dx. So what is that? Remember, you're adding. If you add 1 to 1/2, it's 3 halves. But then you have to divide by the same power, so you're dividing by 3 halves.
Multiply by 2/3.
Which means you're multiplying by 2/3, you guys. Dividing by 3 halves is the same as multiplying by 2/3.
Because of the whole reciprocal rule.
Yep, plus c. So for this section, I don't think you'll have to be much more clever than that. So, let's try some examples. Those were just, yeah, I guess they were examples.
13, 14, 15.
Okay. Give me some ideas. You guys have now become the teachers, and I'm the student.
All right.
You're gonna teach. We're gonna teach you.
Instead, you're gonna change that.
Give me some ideas.
The x plus 1 times the negative 1/2 power x to the negative 1/2 power.
Okay. Okay. Hold on. So here's an idea. You guys see if we should run with this or not. Kate's idea was to change this into x plus 1 times x to the negative 1/2.
Now we have to do product rule.
Yeah, let's not do Kate's way.
Well, where could we go with this? I mean, it might not turn out to be so bad.
Yeah, it'll turn out pretty bad.
Wait, couldn't you do this? Does it work?
Close. Close.
Can we just like try to solve it in our heads?
Wait. Shh. Hey. Go ahead. You mean distribute? So what if we multiplied that through now?
So you get x to the whoa.
So x
To the
negative 1/2.
This is not above you guys' level, you guys. You should be able to follow this. What if you multiply x to the negative 1/2 times x to the 1?
It's x to the negative 3/2. I'm just kidding. It's x to the 1/2.
X to the 1/2.
Why is it?
Oh, because you add
the x.
You're adding exponents, right?
Yeah, that's right.
Oh.
And that's just x to the negative 1/2
And that's x to the negative 1/2.
dx.
So would it be?
So couldn't we separate this now into different integrals?
Yeah, you could. It's not integration. It's separate. They shouldn't call it integration. They should call it
First you got
separation.
integration, you got segregate, and then you move.
All right.
That's not cool, Mr. Up.
All right.
Tag team.
That's now recorded, so they can use that against me in a court of law.
That's unfortunate.
I hope so. So what's the integral of x to the 1/2? We just did that one.
X to the 3/2.
It's x. It's 2/3. Yeah, it's 2/3 x to the 3/2.
Let's see.
And then we add the other antiderivative.
Which is, you gotta go back x to the bottom.
I would actually keep it here.
Oh, okay.
It's going to be x to the 1/2 over 1/2, which is multiplying by 2,
Yeah.
plus
C.
c.
And then you gotta simplify that. Which gives you x squared, which is 4x.
So from here on out,
Things get easy.
4x squared over 3 plus c.
just by glancing at it in that form, what would you say?
4x squared over 3 plus c.
Oh, well.
Maddie, what's your question? This one? So when you take the integral, you add 1 to the power. So negative 1/2 plus 1 is positive 1/2. But then you have to divide by that same power. Dividing by 1/2 is 2.
Because the reciprocal rule.
If you're looking at it like this, are these like terms?
Which I was on.
No.
So I personally would be okay if you left it like this. Let me show you what the book has as an answer.
What? What's this book been doing?
You guys following?
That's the same.
No, it's not. It looks different.
It's the same.
It looks different.
It's the exact same.
It's not the same if it looks different.
Yeah, Gabe. We've been saying that all year.
Go back to pre-calculus.
You know what the same.
Okay, and then they did this.
Go back to pre-algebra.
You watching?
Gosh, those the nerdiest
Whoa. Wait.
What?
Now you just too far.
I got the first one.
Yeah,
I got the first one, but the second one makes 0 sense.
How did we get to this?
Oh, we found the derivative again. We factored out a square root of. No, we factored out a 2/3 square root of x.
They factored out a 2/3 square root of x. This is what you would see in the back of the book as an answer. I would take this on a test.
Which one would you take?
I want it to be add those two things together to get.
You can't add these because they don't have the same exponent. Anyway. Oh, just, you guys, this was okay, what we did. What about this, though?
You gotta multiply to get rational.
You guys, take a look at this. You guys ought to be able to have a little bit longer attention spans than my sophomores. Come on, focus. Look at what I did here. Are these the same?
Yeah, they are.
Would this have been any easier than bringing it up? It's the same thing, but it's a different way of doing it. You might have found this way to be easier. I don't know. You would have ended up with the same answer. Okay, but this is one of these techniques that you would actually use. If you have one single term in a denominator and multiple terms in the numerator, couldn't you split that up into separate fractions? That's an integration technique that you use all the time. You want to log that away somewhere. If you have one single term in the denominator, multiple terms in the numerator, you can just split it up into separate fractions and integrate each fraction separately. Okay. This you're gonna love. Actually, close your eyes. I don't want to spoil the surprise.
Fine.
You're gonna love this one.
Tell me when.
Running a couple minutes early.
I love surprises.
I gotta go check that out.
Wait, let me try one. Give me one. Give me the one.
All right, close your eyes. You can't see this.
Alright.
I wanna surprise you. You guys are peeking.
I'm not.
You guys aren't even close.
My mom taught me that peeking is wrong.
Tell me when. I'm like the best at that trampoline game, dead man.
Boom.
I never beat.
Take a look. Okay.
I almost took it in three.
I've gotten feedback, and it's good feedback. I think it was great feedback, but I've gotten feedback from a lot of you that we need to do more trig.
No.
So
Good one. That was a great joke.
here we go.
Wow, that was awesome.
This is not above your level. It isn't.
Can you change up the sin x and secant square x?
Along those lines, that's what you need to think about. Yeah.
You change it to 1 over.
I'm gonna be like Master Uguay. You just need to believe. Promise me that you will believe.
It's hard. It's hard for you to say yes right now, man.
Kung Fu Panda.
I know, but it's you're not a turtle.
So Uguay was just some crazy turtle after all?
Yeah.
What is it? What's the other flavor?
Come on, come on, come on. I want you to figure this one out.
Well,
I want you guys to figure this one out. You can work as a group.
Okay, guys.
If you want to put your heads together and use all 4 of your brain cells, I'll make 8 brain cells.
Brandon, tell me. What are you doing?
Yeah, but
Yay, this one was good.
Danny, I think your group was the first one that got it.
Cosine squared of x on the bottom is the same as cosine of x squared. So I just split those two apart. And then sine of x over cosine of x is the same as tangent. And then I split the fraction apart more, so then I had tangent of x times 1 over cosine of x, and 1 over cosine of x is the same as secant.
So kind of like this.
Yeah.
Do you guys see what happened there? Cosine squared, you guys just cosine times cosine. So you change that into 1 over cosine times sine over cosine. Are we all in agreement that this is the same as that?
Yes.
We all agree?
We're just missing a dx.
Yeah, there's a dx here. Then what is 1 over cosine?
Secant of x.
And sine over cosine?
That's tangent.
Now I know they haven't been committed to memory yet, but look back at your basic integration rules.
We have one of those.
The integral of secant tangent
Is secant x plus c.
is secant of x
Oh, well, that's
plus c.
I was close. I just had an extra turn.
How does secant tan over
that was close.
Alright, we gotta fly through this particular
Oh, forgetting
particular solutions. Okay.
That's what I did.
You guys done yet? Am I just a big bother to you guys up here?
No, I like you, Mr. You're safe.
Am I interrupting you guys? Okay. So I can feel a seating chart coming on here.
Oh, hey.
So the integral of 3x dx. What did we say that was? 3x squared over 2 plus c. That's what's known as a general solution. Didn't we talk about that already? A particular solution involves actually finding out a value for c. And it's not just random. You know, so c equals 2 or c equals, you have to find out a particular value for c. That's called a particular solution. You see where we're going with this? Okay? So what you need to have is called an initial condition. Okay? So, let's say we want to find the particular solution to dy dx equals 3x squared minus 1 with the initial condition that capital F of 2 is equal to 4. Now, first of all, what is let's keep things straight here. What's capital F?
It's the original. Antiderivative.
It's the antiderivative. So whatever we come up with a general solution to this, that's capital F. You with me?
Yeah.
Okay, but we have an initial condition that when x equals 2, y equals 4. That's going to help us find a particular value of C.
Whatever that is, we'll have to add whatever it looks like.
Yep.
Okay.
So first of all, let's deal with finding the general solution to this. That's finding a general solution to a differential equation is just integration.
Split it up first.
So dy is equal to 3x squared minus 1 dx. Now I don't want dy or dx. What do we do there?
We got a irrigation.
Integrate.
Integrate.
So y is equal. Let's try to speed this up. We know that we're going to be able to separate this into two different integrals. Let's just imagine that we've done that. What's the integral of 3x squared?
It is 2/3 x to the third.
Is it not? Is it not just x to the third? What's the integral of 1? The derivative of 1 is 0.
That was a good try.
Wouldn't it be minus x?
Fabulous try.
Now how do we verify that? What's the derivative of negative x? Negative 1. So the integral of negative 1 would be negative x. But we'd have to put a plus c, because this is the general solution. So now I'm going to call this, instead of y, I'm going to call this capital F. Capital F is equal to x to the third minus x plus c. But we know that capital F of 2 is equal to 4.
Put in 2 for all the x's. And then you're going to solve for c.
Do you see what's happening here?
I do see what's happening.
I want. So what is this going for?
X.
That's an x value.
8 minus 2 is 6.
All right.
And then you
And then this, where does this go?
where that big capital F of x.
That's capital F of x. Okay. So capital F of x, that's going to be 4 equals 2 cubed.
8.
8 minus,
6.
so it's me minus 2, yeah. Plus c.
6.
It is 6.
Skipping steps.
8 minus 2 is 6. If you subtract 6 from 4,
Negative 2.
you get negative 2 is equal to c.
So your particular solution
So the particular solution is y equals x to the third minus x
minus 2.
minus 2. That's the particular solution.
Nice.
We all right? I know that was a lot.
Thank you, Mr. Huff, for teaching.
Okay, we're done.
Guys, wait. Okay.
It's recording.
Math is a wonderful thing. Math is a really cool thing. Screamo! No, you're out of mind! So get off, so let's do some math. Come on, math. 5 minus 3 minus 4 is negative 1.